On the AP exam, there will be 4 free response questions. This video is modeled after FRQ number 2. Let's pretend it's from the 2008 exam. This problem is primarily about exponential modeling and average rate of change. If you appreciate this content, please give it a like. Marie Curie first discovered radium in 1898. After isolating pure radium, Curie was awarded her second Nobel Prize in 1911, becoming the first person in history to win 2 separate Nobel Prizes. A group of scientists began studying a particular sample of a radium isotope called radium-224. After 2 days, T equals 2, there were 3.42 grams of radium-224 remaining in the sample. After 15 days, T equals 15, the sample contained 0.29 grams of radium-224. The amount of radium-224 remaining in the sample can be modeled by the function R, given by R of t equals a times b to the t power, where R of t is the amount of radium-224 in grams remaining after day t, and t is the number of days since the scientists began studying the radium-224 sample. A. Part 1. Use the given data to write 2 equations that can be used to find the values of constants a and b in the expression for R of t. Every input-output pair can be used to write an equation. For example, if we plug in the input value of 2 in the model, it should equal the output value of 3.42. So the first equation is a times b to the second power is equal to 3.42. Similarly, this input-output pair leads to the equation a times b to the 15 power is equal to 0.29. A. Part 2. Find the values of a and b as decimal approximations. The graphing calculator does have a regression model that fits the form a times b to the t power. So that's one method for finding a and b. We could do a regression model. This will not always work because on the AP exam, they will often give you something slightly different than this. For example, it might be a times b to the t plus 1 power or something like that. In this case, you could not use the regression model and you'd have to do it mostly by hand. For that reason, I'm going to show you both methods, starting with the method where you do as much as you can by hand. Starting with the blue equation, we can get a by itself by dividing both sides by b squared. That gives a equals 3.42 over b squared. Now we can substitute this expression in for a in the red equation. So the red equation becomes this, but the b squared in the denominator will cancel out 2 of the b's in b to the 15th power, leaving b to the 13th power. So the red equation becomes 3.42 b to the 13th power is equal to 0.29. Let's get b closer to being by itself by dividing both sides by 3.42. So we have b to the 13th power is equal to 0.29 divided by 3.42. We can isolate the b by raising both sides of this equation to the 1 over 13 power. On the left side, you get 13 times 1 over 13. So these cancel each other out, leaving just b. We can find the decimal approximation for b by typing this expression into the graphing calculator. Make sure you know how to make a vertical fraction on your calculator. One way is to hit alpha y equals enter. Or if your software is up to date, try hitting alpha x, and that might do it even faster. Anyway, in the numerator we have 0.29, and in the denominator we have 3.42. And this is all being raised to the 1/13th power. and hit enter. So this is the value of B. The College Board will accept 3 decimal places, but students often will lose a point by trying to round and then they round incorrectly. So I recommend always using 4 decimal places and never trying to round. I'm going to put B equals 0.8271. Kabam! We are going to need this value later, and we don't want to lose any accuracy. So let's store this value into letter B on the calculator by hitting store and then alpha B. Now we can use this expression to find the value of A. It will be 3.42 divided by B squared. Let's make another vertical fraction and do 3.42 divided by, and because we stored all of the decimals into the letter B, we can do alpha B and then squared. This is the value of A. Let's write down 4.9991. That's it for part A. If we were going to move on from here to part B, we would have to enter model R as Y1 using the values of A and B we just found. We do not want to lose any accuracy, so we will not be using any rounded values of A and B. Since we stored the full values of A and B as letters A and B, right now we can just type in alpha A times alpha B to the t power, but we have to use x. So that's it. However, before we move on to part B, I'd like to go back and show you how to find the values of A and B using the exponential regression features of your calculator. Here are the 2 input-output pairs in table form. Let's enter this table into the calculator. Hit Stat and then Enter. And enter the input values in L1 and the output values in L2. Next hit Stat and switch to the Calc menu. We want exponential regression, which is way at the bottom. So it's right here at option 0. In fact, if you somehow memorize that it is option 0, you can just type 0 next time without scrolling down. Anyway, always tell your calculator to store the regression model in Y1 by going to this position and hitting alpha trace enter. Now hit enter a couple more times and the calculator will find the regression model. Enter, enter. And there it is. Notice this is the same value for A and B that we found the other way. And notice that if we go back to y equals, the model for R of t has been entered as y1 with all the decimals automatically. B Part 1. Use the given data to find the average rate of change in the amount of radium-224 remaining in the sample in grams per day from t equals 2 to t equals 15 days. Express your answer as a decimal approximation. Show the computations that lead to your answer. I notice that we're going to use the average rate of change in B Part 2. So let's define a letter C as being equal to the average rate of change that we are about to calculate. That way, if it comes out to be a crazy decimal, we can just use the letter C instead. In Unit 1, we learned that the average rate of change of R of t on the interval from 2 to 15 will be given by R at 15 minus R at 2 divided by 15 minus 2. We know that R at 15 is 0.29 and R at 2 is 3.42. So let's substitute these values in. The average rate of change will be given by this expression. Let's type this into the calculator to find the decimal approximation. The average rate of change is negative 0.2407. Again, always use 4 decimal places and don't try to round. Don't forget the units. The average rate of change of R of t on this interval is negative 0.2407 grams per day. B. Part 2. Use the average rate of change found in Part 1 to estimate the amount of radium-224 in grams remaining in the sample after t equals 9 days. Show the computations that lead to your answer. When they ask you to use the average rate of change to estimate a value, they are indirectly asking you to find the equation of a secant line. A secant line is a line that passes through 2 points on a function. We need to find the equation of the secant line that passes through the 2 points that we used to calculate the average rate of change. In higher level math, we like to use point-slope form to write the equation of a line, because all we need is a point and the slope. For the point, we can pick either one of the input-output pairs that we use to calculate the average rate of change. I'm going to use this point, 2, 3.42. The slope of the secant line is the average rate of change. Luckily, we defined the average rate of change as being equal to letter C, so we can use the letter C in our calculations instead of this decimal. So the equation of the secant line is y minus y1, so that's y minus 3.42, is equal to the slope, which is C, the average rate of change. And then instead of writing x, I'm going to write t, because that's the input value variable. So x minus x1 becomes t minus 2. And this is the equation of the secant line. In order to use it to estimate another value, let's get y by itself by adding 3.42 to both sides. Now we can use the equation of the secant line to estimate the amount of radium-224 remaining in the sample at t equals 9 days by evaluating y at 9, which will equal C times 9 minus 2 plus 3.42. 9 minus 2 is 7, so y at 9 will be equal to 7c plus 3.42. Another reason we wanted to use the letter C instead of decimals is because we don't want to lose any accuracy, and this is a rounded value. We can avoid losing accuracy by storing the full value of the average rate of change as letter C on the calculator. So just hit store and then alpha C and enter. Now we can use the letter C as we type in this expression, 7c plus 3.42. So 7 and then alpha C plus 3.42. And this is the approximate amount of radium-224 at t equals 9 days, 1.7346. That's it for B Part 2. Don't forget the units. B Part 3. If the model R was graphed in the xy plane using a semi-log plot where the vertical axis is logarithmically scaled, would you expect the graph of R to appear linear, quadratic, exponential, or logarithmic? Explain your answer using the properties of the model R and properties of semi-log plots where the vertical axis is logarithmically scaled. You may not have learned this yet because you don't learn about semi-log plots until the end of Unit 3. So I'm just going to tell you what you need to know. An exponential function appears linear on a semi-log plot. R of t will appear linear on a semi-log plot because R of t is an exponential function, and exponential functions appear linear on a semi-log plot. Part C. The lab equipment that is being used by the scientists is only able to detect radium-224 in samples that are at least 0.05 grams. Explain how this information can be used to determine the domain limitation for the model R. Our strategy is to find the time t when R of t equals 0.05. This time will be the upper limit of the domain, since the equipment will no longer detect radium-224 after this. We can solve the equation R of t equals 0.05 using the intersection feature of the calculator. Go to y equals, where R of t is entered as y1. The solution to the equation R of t equals 0.05 can be found by the intersection of R of t and y equals 0.05. So let's hit graph and see what we've got so far. The blue curve is R of t and the red line is y equals 0.05. The intersection point is going to be off the screen to the right. So let's change the window to make x max much bigger. Let's make it 50 and hit graph. Alright, hopefully we are seeing the intersection point in here somewhere. So let's hit second, trace 5 for intersect, and then let's move the pointer close to where we imagine the point of intersection to be and hit enter 3 times. Enter, enter, enter. And there it is, 24.2612. R of t is less than 0.05 grams for values of t greater than 24.2612. So the domain of R of t should be limited to the closed interval from 0 to 24.2612. Or if you prefer an inequality, you can write the interval like this. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.